In this video, we will investigate several more examples of improper integrals of the first type. So as a reminder, this would be integrals of the form, say, a number to infinity or minus infinity to a number. In either case, we evaluate these by rewriting in terms of a limit. So if it's a to infinity, what we do is we think of the definite integral from a to t, which is something we can evaluate with the fundamental theorem of calculus, and then we take a limit as t goes to infinity. Similarly here, for the case when we're going from minus infinity to b. So if the limit exists, we call the improper integral convergent. If the limit does not exist, we say the improper integral diverges. So let's evaluate the given improper integral. Whenever it's an improper integral, our first step is to rewrite as a limit. So this will be the limit as a approaches infinity, the integral from 10 to a of x divided by the quantity 1 plus x squared squared. And now that we've rewritten it as a limit of a definite integral, we will, in a sense, disregard the limit for a moment. We'll still rewrite it at each step, but our focus is going to be on the definite integral. We evaluate that integral, and whatever result we get back, we take its limit. So looking at the form of our integral, the 1 plus x squared and then the x, that indicates a substitution. So for the substitution, we're going to let u be 1 plus x squared, so that du is 2x dx. So 1 plus x squared in the bottom is u. The x dx in the top is going to be 1/2 du. So we can think of the 1/2 as pulling out in front of the integral, and in fact you could even think of the 1/2 as pulling all the way out in front of the limit, if you would like. So we have limits of integration that we need to determine, but what we're going to be integrating is 1 over u squared du. For our limits of integration, because it's a definite integral and a u substitution, we will change them. So for that lower limit of integration, when x is equal to 10, u is going to be equal to 1 plus 10 squared. So 1 plus 100 is 101. So 101 will be our lower limit of integration. For the upper limit, when x is a, u is equal to 1 plus a squared. So our upper limit of integration is 1 plus a squared. So now we go ahead and we evaluate. And remember, at each step, even though we're not using it yet, we're going to rewrite that limit and make sure that we're using good notation. So the antiderivative of 1 over u squared is minus 1 over u, and we're evaluating from 101 to 1 plus a squared. So we plug in u equals 1 plus a squared, so minus 1 over 1 plus a squared, and then we subtract away what we get when we plug in 101. So minus a minus, 1 over 101. And now we are in the ideal position to evaluate the limit. So as a goes to infinity, the 1 plus a squared in the denominator is going to be getting large. So 1 divided by something going to infinity means that this first term goes to 0. And because the limit of a constant is that constant, we're left with 1/2 times 1 over 101, which is 1 over 202. So when encountering an improper integral, as we have here, our first step towards evaluating is to rewrite as a limit of this definite integral. Once you fully evaluate that definite integral, we then go ahead and take the limit. But at each subsequent step in between, we continue writing that limit until we evaluate. So another very similar example. Integral from 1 to infinity means it's an improper integral, and we begin by writing it as a limit. So the limit as a approaches infinity, the integral from 1 to a of the natural log x over x. And observe there's nothing special about using a. You just as easily could use any other variable or symbol that you would like. And based upon inspection, if we look at this integral that we are going to evaluate, we would want to use the substitution u equals the natural log x, because du would be that 1 over x. So it would be just the antiderivative of u, which is 1/2 u squared. So the value of this integral, based upon that observation, would be 1/2 the natural log of x squared. And note, if you're not immediately seeing this observation that we're making, then go ahead and do the substitution. And vice versa, if you look at an integral and you have some intuition as to what its antiderivative will become, you don't need to always include those steps for the u substitution. But never worry about doing so to double check. And we're evaluating from 1 to a. So we replace x with an a. So that would be 1/2 ln of a squared. And then we put a minus sign and replace with a 1. And note that the natural log of 1 is 0, so we actually do not need to write anything down. If you wanted to, we certainly could. Minus 1/2 natural log 1 squared, and then just observe ln of 1 squared is 0. Now as a goes to infinity, we're thinking about what happens to the natural log. Well, recall our graphical perspective. The natural log looks something like this. So as x goes to infinity, the natural log of x goes to infinity. So similarly, as a goes to infinity, the natural log of a goes to infinity. So in this case, we would say that the improper integral diverges.